Well, I've had lots of emails about homework number 2, so I decided to make another video on trying to give you guys some help about strategies on helping you guys out with homework number 2 and what you're supposed to do. So the first big questions I've had on a lot of those emails is they're not sure how to show things like GCDs and the like. So I want to remind you, Theorem 1.2, what it says. It says this: given that the GCD of A and B is equal to D, and of course A, B, and D are all integers here, then there exists integers, favorite letters, U and V, such that A, U plus B, V is equal to D. And remember about these integers U and V are not necessarily unique, but you can go from a GCD to an equation. The GCD of A, B equals D implies that there exist integers U and V such that AU plus BV equals D. So you can go from GCD, listen to my words, you can go from a GCD to big equations, because you guarantee there's going to exist these integers U and V, not necessarily unique. And the other deal is, when it comes to GCDs, the other option you have is the definition of GCD. And when the definition of GCD, really what you're focusing on is the actual CD part of it, common divisor. So if you were given the GCD of A and B is equal to D, then D divides both A and B. And by definition of divides, there exists integers U and V such that, or well, X and Y, because I already used U and V. X and Y, I'm trying to do a little different letters here. There exist integers X and Y such that, now D divides A and D divides B. A and B are bigger, so A would be equal to dx and B would be equal to dy. So let's look at the strategy here. When you've got GCDs, you really have two options with them. You can actually go for that theorem 1.2, which means you can take the GCD and you know there exist integers U and V such that AU plus BV equals D. You can get a big equation out of this guy. Or you can use the definition of GCD, which is really focusing on the CD, the common divisor part of it. So the definition of GCD says given that the GCD of AB equals D, then D divides both A and B. But you need that equation stuff. So then by definition of divides, there exist integers X and Y such that A equals dx and B equals dy. You get little small equations. Small equations are great for substitution stuff. Big equations are great for getting that equation that you need when you want to show somebody divides something else. Because you already got that big equation typically equal to D. You can multiply both sides by stuff. You can substitute stuff. And so this is the big equation you typically want to manipulate. The GCD definition gives you the small equations that you typically want to substitute in. But now, I also want to remind you of a slight theorem I put on one of my videos. This is one of my theorems that I called it, and I called it Theorem 1.2b. 1.2b dealt with the GCD of A and B being equal to 1. A and B being integers, and they're relatively prime. And it went like this. And I started out given A and B are integers. it's understood when I'm playing in this world that everybody's an integer at this point. Don't worry, chapter 3 is coming down the road when we change that. But right now, everybody's an integer. So given that A and B are integers, then the GCD of A and B is equal to 1 if and only if there exists integers. Go back to my favorite letters, U and V, such that AU plus BV is equal to 1. Now, what's the difference between this definition, or this theorem 1.2, B 1.2? Well, in theorem 1.2, way up here, when I talked about it, you've got to have a GCD, and that implies that you can get an equation out of it. Just because you got an equation doesn't make the GCD of an A and a B equal to D. That's not how it works. This is a one-way implication. If you got the GCD equal to D, then you can write an equation out of it. Theorem 1.2 is because they're relatively prime. Now remember, GCDs are always positive integers, and the smallest positive integer is actually 1. And because if you got two integers, A and B, that are relatively prime, the GCD of AB equals 1, and it basically it's the only time your equation can go both ways. If you got that, then implies that they're just integers U and V, so it's AU plus BV equals 1. But you can also go the other direction. If you actually have an equation where A times U plus B times V equals 1, then you can actually go back and declare that the GCD of AB has to be equal 1, because 1 is the smallest integer. I can also tell you from this equation, and the GCD of A and B is 1, the GCD of A and V equals 1, the GCD of U and B equals 1, and the GCD of the U and V is actually equal to 1. One integer from this term and one integer from this term would actually have a GCD of 1. And it's because 1 is the smallest positive integer. Now, one other definition you need to know, and that's this, quote, A is congruent to B mod n, modulo n. Written like this, and this equation is perfectly fine to have in your proof. Remember, you're not allowed to actually divide with a little divide symbol. You got to write. This is a writing intensive class. It's about math proofs, and math proofs about writing it up, not using symbols and shorthand notation and abbreviations and stuff. So you are allowed to have this type of congruence equation, but you want an actual equation out of this guy. So A is congruent to B mod n, and written like A with the three little equal signs here, 3 little bars. A is congruent to B mod n means this. Means that n divides A minus B. That's actually the definition. But to actually get it back down to an equation here, you've got to go a little further. And then you've got to do this. Then, by definition of divides, there exists an integer. Pick my favorite one I haven't used it on. W, such that we'll run an equation. If n divides A minus B is bigger, so A minus B would be equal to n times W. And there's your equation, and then you can go and manipulate your equation however. But it actually takes two definitions. Two definitions here. You've got the definition congruence modulo n to get that n divides A minus B, and then it takes the definition of divides to actually get the equation A minus B equals NW, and that's the way you have to write it up to get it down to the equation level. The goal in all these proofs, and these direct proofs that we're using here, is to write this stuff up to get it to an equation level, and then manipulate the equations, and then rework back the theorems and the definitions to show that A divides B, or the GCD of A and Z is 1, or something like that. So let's take a look at the homework set real quick. All right, on this particular problem, and this is another one right out of your textbook here, let A, B, C be integers such that if the GCD of A and C equals 1 and the GCD of B and C equals 1, then prove that the GCD of AB times C is equal to 1. And you want to prove it, not just clearly and obviously type thing here. You want to actually do a direct proof. So I'm going to come down here, right halfway in the middle of the page, and do my famous WTS. Now remember, this is the stuff I'm not going to turn in. This is just my scrap sheet of paper. And then, because then we're going to figure out the technique and how to write this stuff up. And then I go write it properly, with no symbols, anything, paragraph form, neat handwriting, quoting the correct theorems and definitions and stuff. So in this particular problem, I want to show, WTS, I want to show the GCD of A times B, comma, and C is equal to 1. The GCD of A times B and C is equal to 1. How do I show that? I get to show that, and remember, this is my scrap sheet of paper, so I get to put all kinds of symbols and stuff like that. I get to show that, honestly, by Theorem 1.2b. That's because basically I'm trying to tell you, I'm trying to show that A times B and C are actually relatively prime to each other. Well, Theorem 1.2b says that there exist integers, there are integers U and V such that A times B times U plus C times V is equal to 1. That's my strategy right there. And I'm going to have to figure out what the integer U is and what the integer V is. And once I get these guys as integers, then from that equation, and Theorem 1.2b says that the GCD of A, B, and C is actually equal to 1. So that's my goal. Now, before you want to show, you've got the givens. What's given on this thing? Well, your givens are, the first one is that the GCD of A and C is equal to 1. And then you can start with by Theorem 1.2, because the definition of GCD, 1 divides, it's not going to really help you out at all. 1 divides everybody. So by Theorem 1.2, there exists integers, P and Q, such that AP plus CQ is equal to 1. I got an equation. Also given that GCD of B and C is equal to 1. And again, when they're relatively prime, you only got one thing, and you can quote Theorem 1.2 or 1.2b, because 1.2b actually goes both directions. So by Theorem 1.2b, again, there exists integers x and y such that bx, get my right letters here, bx plus cy equals 1. So these are the two equations I can get from Theorem 1.2b, because we're talking about relatively prime here. I got to manipulate these two equations to get this equation. And the real hint is going to be, well, I still want it equal to 1, but I want an A times a B with an integer and a C with an integer. Well, if I do this and do basically 1 times 1 equals 1, I can put these equations. And so here's your last hint on this one. Basically what you need to do to manipulate this guy, well, since 1 is equal to 1 times 1, then 1 is equal to, slide up, you guys can see this, AP plus CQ times BX plus CY. And that is just by substitution. Always your statement and your reason here. Now with this one, you could FOIL, also known as distribute. I want you guys to get used to your big terminology here, not just by algebra. I want more into it. So I'm going to start requiring you to tell me what algebra you're doing. Foiling is okay, but that officially is the distributive property. It's just a lot more than just basic algebra here. And then I'm going to FOIL this thing out. And then I'm going to group together like terms and factor out, because my goal is to get this equation as 1 is equal to AB times some integer plus C times some integer. This is my some integers. This one needs to be some integer. And just like you did in the last homework set, which by the way I posted the solutions for, you can sit there and basically, well, since x, y, u, and v are integers, then whatever that happens to go here is an integer. And since this, a, b, c, and u and v are all integers, then this guy is going to be an integer. And then you can quote your Theorem 1.2b to actually go back the other way and actually tell you that the GCD of this of A, B, and C is actually equal to 1. So that's the trick on this guy. Is actually the fact is that 1 times 1 equals 1, and that Theorem 1.2, and I call B because Theorem 1.2b basically goes both ways. You get an equation equal to 1, you can actually declare who's the GCD of what two guys is going to be equal to 1. And if you've got two guys, two integers equal to 1, then you can also write an equation equal to 1. Now this one right here, you've got to think about what you want to show. On this problem, it says let A, B, C, D, and E, pretty much everybody, is an integer with A not equal to 0. If the GCD of A times B and A times C is equal to E, and the GCD of B and C equals D, then I want you to show E divides AD. Now be careful. All I ask you to show is E divides AD. The fact is E equals AD. So you can easily show that AD divides E, but you showed the wrong way. So it's very important. I want to show, so here it is, want to show. I want to show that E divides AD. Now remember, this is my scrap sheet of paper. I actually have to write the word divides on my proof, otherwise you're going to start losing even more point totals than you did on the last one. Here, it's a writing intensive class. But E divides AD. What does that mean? What I really want to show is that A times D equals E times that famous some integer, and I got to come up with who is that integer going to be based upon the givens. Now, let's come up here. Here's your strategy. What are the givens? You're given two things. You're given that the GCD of AB and AC equals E, and you're also given the fact is that the GCD of B and C is equal to D. Now remember, with GCDs, you got two options. So the first option is Theorem, and I want to abbreviate Theorem 1.2. You're going to get in here, not allowed to use that on actual write-up of official proof there. That means there exist integers. Pick your favorite guy. There are integers. There are integers P and Q such that ABP plus ACQ is equal to E. That's one way. Or you can use the definition of GCD, which is that E divides AB and E divides AC. And by definition divides, there's going to exist integers, and I can use different letters, X and Y, here that AB is equal to EX and AC equals EY. I can either have a big equation or two small equations. In the same light, I can come over here and talk about the given of the GCD of B and C equals D. I can go from this and go by Theorem 1.2. There exists integers alpha and beta, just to completely throw you off with some Greek letters here, such that you have B alpha plus C beta is equal to D. I can have a big equation. Or you could sit there and go that definition of GCD route. And with the definition of GCD, that means that D divides B and D divides C. And by definition of divides here, there exists integers, stick with the Greek letters. Let's see, theta and phi, such that if D divides B, B is bigger. B is equal to D theta, and C is equal to D psi. So I've got two small equations. Now, some of this stuff I'm not going to be using. My goal here is to show that E divides AD, which means I need an AD equation. So based upon all this stuff, how am I going to get an AD equation? Well, you're going to get an AD equation. See, this is an equation, great, but it said equal to E. I don't say equal to D. I want it set equal to AD. I want to see that AD equals E times some integer. I want to be able to factor out an E. I don't want to set it equal to D. So I don't want to use this one. I think I want to use this one. So if I can sit there and have, do this route, and we have the equation B alpha plus C beta is equal to D, but I want to be able to factor an E out of it. Well, first off, I want to set the equation equal to AD. Well, D is good, but it's not AD. So what I'm going to have to do is multiply by A on both sides. So I end up getting A times B alpha plus C beta is equal to A times D, and then I can distribute AB alpha plus AC beta is equal to AD, and that was this distribution property. Again, we want you to use words like associativity, commutativity, distribution. This is what we're after as we're getting into the bigger heart of ring theory and the like. So I got this big equation, but I need to factor let's see, an E out of this guy. So to factor out an E out of this guy, okay, I want to be able to put an E into this guy. And you notice that with this, AB can substitute for EX, and AC in for EY. And I got an AC and I got an AB. So I want to use this one and not the other guy, the GC definition of GCD with the small equation here. I want to use Theorem 1.2 on this one, so I don't want to use the definition. So don't write these parts up in your proof, because if you don't use it, I don't want to read it. But we're going to use this guy and this guy. And then I can sit there and plug in for, like I said, using this, I can plug in for AB, EX. You end up getting EX alpha, plus, and plugging in for AC, I can plug in an EY, so it'll be EY times beta equals AD, and then I can factor out my E. It'll give me X alpha plus Y beta equals AD, and since all these guys are integers, the whole thing's an integer, and then I can use the old definition of divide. So this is the definition of divide. So that's the strategy, but now you got basically it's a game of picking out the direction you need to go and connecting the dots. I want, given the GCD of this guy, I want to use definition of GCD. Given the GCD of this guy, I want to use Theorem 1.2, and then take the information and start manipulating the equations to get the equation that you want. AD equals E times somebody, and then state why that somebody is an integer. By definition of divides, it's an integer. Okay. This one right here, this one is about as straightforward as I could possibly make it. But this one, I'll show you some ways of actually kind of shortening your proof here. Because you are given, so I can start out with the given, which is A is congruent to B mod N. And you're also given that C is congruent to D mod N. It's the same mod N for both of them. If I change to a different integer, that's a different modulo. If that was an R and an S, I would have to do those guys separately. But since it's the same mod N, I can put them together. So given that A is congruent to B mod N and C is congruent to D mod N, then by definition of GCD, remember I'm abbreviating this stuff, not GCD, congruence modulo N, by definition of congruence modulo N divides A minus B, and N divides C minus D. Remember, you're not allowed to use a symbol on this one, but this is my scrap sheet of paper here. And then by definition of divides, and again on an actual writing proof you can't abbreviate definition or whatever, but by definition of divides, there exists integers, x and y, such that A minus B equals nx and C minus D equals ny. Now, what do I want to show on this guy? I want to show that A plus C is congruent to B plus D mod N. What does that mean? This is actually the definition of congruence mod N, modulo N. Okay, what does that mean? That means that N divides A plus C minus B plus D, and notice the wonderful use of parentheses there. And to be able to show this, this is that definition of divides. What we want to show is that A plus C minus B plus D is equal to N times some integer. Again, this is not the official write-up. I'm just talking about strategies here. Your write-up should be a classic paragraph form without the symbols and stuff, except for the equations and the congruence classes. Those are legal. You won't be going to write as equations. So how do I take this guy and actually come up with this? Well, I really want is A plus C. We're talking about addition. So I could start with this guy and add ny to both sides, and then replace the ny with the CD, so I get A minus B plus C minus D is equal to nx plus ny. And then I can group them together. That'll be A plus C minus B minus D. I can factor out the negative, and use words like factor, that's good. You end up getting something like this, and it's equal to nx plus ny. Factor out the n, and then you've got some integer. But then you've got to back it off. To show congruence, you've got to back it off. Once you've got the integer, you can sit there and say that therefore n divides A plus C minus B plus D, and then back it off one, therefore by definition congruence modulo n, and then you can say A plus C is congruent to B plus D mod n, because it's a two-step process to go from the modulo n style of equivalence class to actually equations. You got to do the definition congruence, which gives you the divides, and definition of divides gives you the equations. Okay, but all you got to do is just add them up. Now the last one should be straightforward, and I bet a lot of people were complaining. So let me give you a hint on this one. Now this is that algorithm using the GCD. So the Euclidean algorithm is the idea is we're going to do that long division. You're going to get 300. That should be 3,612 is equal to, you're going to divide it by 816, and you actually don't have to show me the division, but you do have to show me this equation is equal to somebody plus a remainder. And then the Euclidean algorithm you're supposed to shift. So here comes the 816 is equal to the remainder, I'll just call him R there, is going to come over here, and then you're going to figure out what the quotient is by taking that remainder divided 816, and it's going to be plus another remainder, and then you're going to shift here, and then do the same thing. And you should only have to write this thing out 4 or 5 times at most. I mean, 5, if you write 6 or 7, you would have done way too much. So it should be around 4 or 5 times, because the goal here is you want to get it down here where you have somebody is equal to somebody times the quotient plus the remainder of 0. Because once you get the remainder of 0, the remainder before the remainder of 0 is actually the GCD. This remainder would end up being the GCD guy here. That was, just to remind you, that was Euclidean algorithm. Now the other thing I want is to finish up that concept of Theorem 1.2. I want you to tell me who U and V are going to be. Find the integers. So at the end of the day, I want you to tell me U equals this guy and V equals this guy. These guys are not proofs. These guys are manipulating equations. But remember what we talked about is you take this equation, solve for the GCD by moving this stuff to the side, and then you substitute in this equation, then you substitute in this equation, and then you eventually substitute in this equation as you group together like terms, and the really only 2 terms you want to focus on are the 3,612 and the 816. And once you get that equation, you put all your little terms together, you can figure out who the U and the V are going to be that make that equation. So as I try to give you something that wasn't so proof-oriented, because I do plan on doing the same thing to the test. So I've got this one doing. I'm going to make it do. I did. Some students did ask to push it back just a little bit to give them some more chances to play with this thing. But at most, I'm going to do is just before class. Class starts on 3 o'clock on Wednesday, so I'll push it back to 3 o'clock on Wednesday, and then after that, 3 o'clock on Tuesday, because then after that Wednesday, we're supposed to have our test review. And what I'm going to have you guys do for a part of your test review is, I've already got your homework number 3 up, waiting for you guys to work on that one. And between homework 1 and 2 and 3, that's where the style of question is going to be coming from for my test number 1 that covers chapters 1 and 2. So I am going to push this one back. Instead of being at 11 o'clock tomorrow night, I'm going to push it back till the following day, just before our class starts at 3 o'clock. You got to get in. I'm going to have a hardcore deadline on that. And then I want to post a video solution for that. And then that night, and you keep on working, I'll have the other one due just before class at 3 o'clock on Wednesday. And we'll actually go over that as part of our review. And I'll talk more about strategies and things I'm actually going to do on the test, or what the test makeup is going to look like and stuff like that. And then we'll move on a little bit. Go ahead into chapter 3 and get hard into chapter 3, because hey, this is summer school, we can't afford to wait. But your test 1 is only going to be on chapters 1 and 2. Hope this has been helpful. Thanks.